Hi everyone, welcome back. Just had a good chat, so let's get it rolling. As always, I know you all more or less personally, but if you don't feel like being on YouTube, you better hide yourself right now. All right, the topic today is databases. As I already made the disclaimer, I do not consider myself a database expert. Quite a few guys are far more experienced in databases than I am. So instead, I'm going to frame this more like an OLTP/OLAP conversation in a system design fashion. How to choose where to use which databases, which pitfalls to avoid, what are the good patterns, where SQL fits, where, let's say, BigQuery, Snowflake, or whatnot fits, how to use and not use Dynamo or Spanner. Hopefully, we can cover this in some detail. I do have some slides, and I'm going to go through them right now, for which I'm going to share my screen. All good? Alrighty. So we're going to talk about databases. And by the databases here, I mean the part to which the application server talks to while serving user queries. So it's presumably real-time. I'll define OLTP and OLAP in a moment, but basically this episode is not about OLAPs. If it's about analytics for you, if it's about large-scale, batch, slow-ish queries, which is something that the data warehouse, data lake backend would do, this is mostly out of scope today. OLTP, as I understand it, is the database, or actually could be a bunch of databases, that are used many times per second in real time to serve user queries. So the bottom line is it's supposed to be a super high performance in terms of TPS, transactions per second database. If you want to do a full scan on an OLTP database, either you're a small startup that is just starting, or you're doing something very wrong. I mean, unless you build a search engine for which you would need to use something like Elasticsearch or build your own Elasticsearch, we're not going to cover this right now. Of course, it's all context dependent. If you're an internal revenue service, that's United States Tax Department. If your query time is like weeks and the response format is not HTTP response but a paper envelope, you could probably build your system using Hadoop as a backend. You don't care if the query or update takes hours. In most applications we build these days, you do care about this. So the majority of use cases of databases in this regard are the low latency, high throughput ones. Most of us, when we will be building or designing something, we will need to choose a database. And the way it works is, honestly, it's mostly an administrative decision. You need to figure out which database to build your service on, because later on, your developers, your original developers, and then the people you hire, potentially some third-party developers, will be building applications on top of this database. And when you need to make sure your service can be scaled by orders of magnitude in the numbers of users and requests, in the volume of data, and you also want to make sure this service can handle tight SLAs and be highly available, that's where it becomes really important to make sure you pick the right database. By database here, I don't just mean we're going to use MySQL. I mean the whole spectrum, the whole constellation. Whether you use a SQL database, whether you use a cache, whether you use the, let's say, Kafka message bus as the persistent event bus, which is the source of truth. All this in my head so far qualifies for a database. I've tried to outline the requirements for this selection, for this choice, and I came up with 3. In no particular order. The order is actually messed up intentionally. One requirement is the scalability, as it's commonly said today. I mean, honestly, it's actually a big point to be made here. Every single large company was a small company at some time in the past, unless it's a government-sponsored huge project, which don't happen often these days. Every large company was a really small company with a bunch of hackers. So every single company I work with, there are people who would say, oh, bad decisions were made 20 years ago. If only we did it the right way, and I know what the right way is, we would not be dealing with this mess today. And when I have to talk to these people and work with them, I always have to explain them carefully that, look, it's actually a stable, healthy approach. Because if you build the things the right way from day one, it would take 10, 20 times longer to build a prototype. And most companies, most product ideas fail. So it's actually a better state of the art where things are built in a slow and hacky ways and then potentially rebuilt, and then tons of legacies to be maintained. As a humankind, we win. As engineers, we have to suffer, but there's no perfect engineer in heaven, at least not that I'm aware of. So after this detour, the point here is that today, a lot of new projects, a lot of new companies, a lot of new designs, the requirement for them is we need to build it so that we can throw money at it if we have to scale. So if it's a small startup, it's in the garage. It probably if it raised some money, it has some Amazon or Google credits. So the first, $100K are free in cloud resources. People are happy throwing money at the solution. People are happy with having totally cost-ineffective designs, as long as if they take off exponentially, they can pay 10x money to get 3-4x performance and throughput. That's without moral judgment, that's a state of the art. The second major requirement is the system should be available. It should be available as in highly available. If something dies, be it your application server or your database node, you should never ever lose data. Ideally, your users would not notice if something is down. It just maybe a potential slowdown in some parts of the world, and then you add more machines and it's back to normal. Again, if you're a small startup, if you're Facebook as suggested at its inception, if you lose a database, you're down, period. These days, it's not the expected standard. And the last point here, which actually is not the last but the first one, is you choose some database, some OLTP. If it's you and your friend, and you guys are really fans of, Erlang or Haskell, you can do whatever. But at some point in the future, you would hire people. And you would hire people who would be building product application features on top of your OLTP stack, database stack. So it's important for your choice of OLTP to not be the bottleneck with respect to how quickly can you hire more people and ship more features. This design for growth is still a good mindset. Assume your company would either fail, assume your product would either fail or succeed wildly. And if it succeeds wildly, half a year from now, you would need to hire 100 developers. Would you be able to teach them? Would you be able to find them in the first place? So I think these are the requirements. This is what is to be kept in mind when you think how to structure the OLTP part. As always, interrupt me anytime. So taking the third bullet point first. So the ease of development, I think, is mostly about engineering practices. That's where I know we're a system design meetup, but system design at high level, I think, has a lot to do with people. So that's where agile, sprints, scrums, ownership, componentization comes into play. And as I said before, just to summarize this, it's a huge continuum. It's a continuum because on the one hand, you have huge corporations that want to make sure every single developer is pretty much replaceable, which means that it's okay if it's slow and expensive, it just should be standardized. On the other hand, you have startups of two people that are trying to squeeze out every single bit of performance because that's what they're striving for originally. In my experience, the vast majority of technologically advanced, technologically bleeding edge products start from the piece of technology which is abusing some of the modern day trends of how to build things, because this abuse of technology is the only way to get past this bleeding edge. So it's perfectly healthy, I think, that the best product that start today, if they are tech savvy. If it's another e-commerce shop, they can be built using best practices because we have these best practices. If it's something technologically savvy, if it's something that was not done before, chances are the early developers would have tons of tricks in their sleeves about which later developers would argue, how could you even think about doing things so ineffectively? Well, it was the only way to do it back now. When it comes to reliability, I feel like, well, let me take a step back. Sometimes one of my hobbies, I would say, is to help people prepare for system design interviews. So I sit in tons of workshops and I see how people reason about how to best design systems in an interview setting. A lot of times people would just say, oh, I have a database. And they would draw a database on the whiteboard and say, hey, I have this database. It's distributed, it's replicated, and my application server talks to this database. That's often not a bad design. But again, it could be my bias. I'm not claiming to be right here. But I view pretty much any product through the lens of what are its data access patterns. And if you ask me about how would I design a web crawler or a large-scale messenger like Telegram or Signal or a search engine, to me it's all about how do you manipulate the data. The application servers are just a thin layer that exposes these access patterns to whatever your frontends are, be they mobile apps, web browsers, native apps, or whatnot. And in this regard, a single database that you just draw as a cylinder on the whiteboard is by far not a complete solution. And in my vocabulary, anything that has to do with storing data that could be accessed as part of the user query time is part of the database. So be it a SQL database, a NoSQL database, and of course there should be different boxes on your diagram if you have to use both. If you have a cache, it has to be a dedicated component. If you have some PubSub stream, a Kafka stream, which in your design could potentially be used as the source of truth, which is often the case. If some component goes down and it restores the state by replaying some Kafka stream once it goes back up, maybe on a different machine, then this Kafka stream becomes part of your database in my vocabulary because it stores the user data. You can have some custom built cache that performs some business logic, which is also part of the database more or less. And quite honestly, you can have a design which stores the data as files or in S3 buckets, and that would be the database for this service. Back at Microsoft, I was working on a project that has to do with doing some computations while the airfare prices are being fetched from another service. And as you guys know, when you book airline tickets, it takes like 7 seconds until the data is fetched. From what I've heard, rumors are this delay is artificial. People are just willing to pay more when they feel like the service was working hard. But the point is, our backend had an SLA of 7 seconds to serve the request. We knew the user is waiting. So we just could store all the data in SSDs, have some indexes, and scan the disk, seek and scan the disk. We didn't have to put anything into memory. So to me, this is part of a database, even though it may have nothing to do with the actual database. Well, finally on slide 8, we get to the word SQL. I'm going to talk a bit about SQL. Keep in mind, I'm not a SQL expert. But I think the biggest takeaway message here is that there's no one-dimensional dichotomy between, let's say, SQL and NoSQL, ACID and base. But I think what would be a good starting point, and again, that's the way I usually recommend people have these conversations if they have to explain somebody else that they know what SQL is. I think there are a few huge points that are somewhat independent, but are covered by the umbrella of SQL. One is that SQL databases guarantee transaction atomicity and isolation. So each transaction either goes through or is as if it didn't happen. You could have transaction isolation levels for higher performance, which would potentially give you dirty reads or phantom reads or whatnot. But for most practical use cases, what you would do is you would use a database in a way that makes sure the transaction either did or did not happen. And the transactions don't know about one another. The database engine is supposed to handle this internally, all the way down to replication and whatnot. One more distinct feature of SQL databases, SQL database engines, is that it seamlessly supports multi-table joins. If your data is normalized, which again is a different topic all by itself, and by the way, I would argue that the modern generation has an advantage over me, because we kind of learned the normal forms at school, and we understand data normalization as the canonical process. But as it turns out, it was a surprise to me at some point. As as it turns out, when you want to use the modern NoSQL databases, you have to unlearn what you have learned. If you want to use DynamoDB effectively, if you want to use Cassandra, React, Mongo, you can do miracles with those databases too, even though hardcore SQL people would argue those are not databases. You can build services using those databases, but the access patterns you would use are entirely different. You would restart and recache the keys. You would store different kinds of values for the same key, and you would tell at runtime that for this particular key the value is as if this key is the, I don't know, user record or a product record or a shopping cart record. There are tons of clever ways to optimize NoSQL databases, to optimize extended key value stores, I would say, to use them effectively. On a level of SQL, you never have to worry about this. You just know you can join any tables, and the result would be a transaction, which would give you the data you need right away. One more important point I would make about SQL is that it really takes away the pain of optimization, largely, both on the query level and at the index level. I have a dedicated, one step back. So when I say optimization, what I mean here is that, again, I'm thinking of data and developers. When I'm talking database optimization, I mean that the developer who writes the code doesn't have to know how is this data laid out on disk and memory and in caches of your RDBMS. So that if at some point you need to add an index so that you can execute some query faster, a special person, database administrator, DBA, who doesn't really know how the code works, this person would just know, hey, these are the kinds of slow queries. This person can optimize the database or hack the database more or less to make this particular query faster. And I know people who interfere with query plans by artificially extending the perceived number of records in a certain table, because that's the way to convince the database engine to use different kind of join techniques. The point here is not that you can have experts who know how to do magic in that regard. The point is that SQL in this case is a really good proxy, because the developer writes a SQL query, and the way the data is actually laid out in memory on disk can be changed at runtime without having to change or even recompile the code. And I think that's a huge, full disclosure, this episode is mostly about demarcation lines between databases and application logic. And I think SQL as a language is a really good philosophical way to look at this, at how can the data access language and data layout be separated. It's not the best one for all the cases, but it's a really good one, and historically it's the first one, I think. Rahul?
I have a question. I might sound like playing devil's advocate, but in the past, I've heard arguments like, joins are very expensive, especially in real-time transactions. So instead of modeling your data surrounding relations, model your data as, a key value pair. The value is like basically represents a document. That's basically going on to a document DB. So my question then is, this very convenient argument, but then how do you counter such an argument? Yes, of course, it's doable. We can definitely do anything under the hood, but should we do it? And if not, why not?
That's actually a great question. Thank you. Well, first of all, I do not believe an OLTP database should have tons of joins, because OLTP is supposed to be super fast and high performance and low latency. So in the vast majority of real-life cases, even if your production database is a SQL database, is a relational database, chances are you would denormalize your data quite a bit for the sake of performance. But then again, yeah, it's a continuum. At some point of optimizing your SQL RDBMS to serve your production needs, at some point you would effectively reinvent a key value store on top of, let's say, Postgres, which is often the best solution. And you would have to question yourself, hey, if I'm going to use my SQL table as a key value store, why not use a key value store? I don't think there's a universal answer. What I think is the answer is that, well, let's put it this way. I believe joins are not that useful for OLTP queries, period. Joins, on this slide, I think joins are a really good differentiator between SQL and NoSQL databases in general, even though these two are kind of convergent. Many NoSQL engines these days do support joins. I think it's just, there are two different schools of thought. There are two different ways of thinking about databases. You can think of a relational database where you normalize your data and the only way to access data would be joins. Or you can denormalize your data so that you can access certain kinds of fields faster, but then you're responsible for maintaining these parts consistent. I think Rick Hooligan, the guy from Amazon, I'm linking to his talk later in the slides, said a really clever thing. It's a super simple thing in the hindsight, but I haven't heard it before him. He said that when you think of how SQL was created as a language and as the database engine, it was the times when the hard drives were super expensive. But slow query times were kind of fine, and CPU was a lot cheaper than hard drives. So data normalization was effectively the only way to deal with tons of data, because if you had to store the same bit of data in 100 places for faster access, the cost of your system would become unbearable. So you had to normalize the data, compress all the fields, and your database tables would be super compact. In the 21st century, the situation is the opposite. Storage is super cheap, and CPU is what we're fighting for. So naturally, when the storage is super cheap, and you're fighting for maximum throughput, minimum latency, and the ease of replicating your data, the ease of building highly available systems, you almost always want to replicate your data to as many machines as possible, because it lets you buy throughput and latency, right? So that's Andrei.
Yeah, well, I would argue with this in the sense that OLTP actually, it's purpose of OLTP to have joins. I mean, and idea behind that, it really, so it's very high level statement. And I think there is not much support on it, because actually it really in terms of architecture, it really depends what task we are trying to resolve. Because if it's about delivering and consistency of the data, or on parallelize those things, the trick is that usually in those databases you have some access layer levels and some supporting structures that if the one that you would replicate or denormalize would take really inefficient space. And also I disagree with the thesis that storage is cheap. Good storage is actually very expensive.
Okay, good points. Let's dive into those. So first of all, in my experience, OLTP, the volume of data you need to access in OLTP fashion is usually not too large. I mean, the majority of if you look at the data you have to operate with in your service, like take any modern large-scale service like Pinterest, like Facebook, the majority of data would be media data, like images, videos, or whatnot, sound, and this data is stored. Like, it's expensive to store it, you're right, but it's not stored in a database. It's stored in a document storage in blobs or something. What OLTP and it's not served by your application; it's served by the CDN. So the OLTP queries would be about the metadata on this data, and the metadata is hardly large, right? I mean, all the bank accounts, for example, are just single-digit gigabytes for the whole planet, or something like this. So I agree that the storage is expensive. I still think that when it comes to OLTP use cases, denormalization is largely preferred because, well, it wins you latency and throughput. I think in my book here, the bigger point is that RDBMSs, well, SQL RDBMSs, by definition, offer you transaction isolation. So there is the extra cost of maintaining denormalized data is close to zero. In my head, so the pain of denormalizing the data is that if you change a bit of data somewhere, you need to make sure all the derived locations are changed too, which does not sound hard, until you have to worry about high availability. Because if you need to be highly available and you change some data and you need to change it in 10 other places and your machine dies, you need to apply the same change by some other machine or by the machine that just restarts. Or you have to implement your manual two-phase commit so that you know which parts to roll back. But your rollback should restore your now denormalized database in a consistent state to a consistent state. And so in my practical experience, if you have like some Redis cache, some relational table, and some Hazelcast for whatever, maintaining these three in a consistent fashion is almost impossible. Like for the vast majority of implementations, it would either be a write-only code that some genius guru wrote 10 years ago, which kind of works, which is totally unmaintainable, especially after this person leaves, or it would with the code that is full of holes and the business is fine with some data inconsistency in case the machine dies in the middle of processing the query. The point here is that if you have the database that guarantees your transaction isolation, and SQL databases are asset databases, then for OLTP use cases, I think in most cases you would actually denormalize your data. I mean, let's take an example. Let's say that you have a normalized, let's say you have a social network, you have a user ID, and for this user ID, I have the URL of the ID of my avatar picture, and I have my full name that is shown there, the display name and the vanity URL, and maybe some top hobbies you would show on the profile page. In a normalized fashion, of course, these data fields would be in some other tables. So to render a profile page, the select query would contain a bunch of joins. But of course, you don't want to make these joins when you render a profile page if you're using a SQL database for your small social network. Of course, you would denormalize this, right? Now, if you change your name, for example, you would need to remember the code that the developer writes that supports name change would have to change the name in more than one place. And yes, it's a source of bugs. You can forget to change it somewhere else. And yes, this developer would have to know the database structure, and the database is maintained by another person, and these two guys or gals may not talk to one another often. So yes, it is a source of bugs. But at the end of the day, throughput and latency win. At the end of the day, you need a service that can scale 2x, 3x, 4x in the next month or so, in which case you have no other means other than to denormalize this data. So you would denormalize the data in a SQL database and have a parallel effort to store this in the key value store, which is a NoSQL database. That's, I guess, my main point here. But yeah, Andre, I agree with you. Next. Unmute yourself, please.
You never completely denormalize the data. In your case, in a scenario, suppose you have a social network, and like no one in a sale, no one in would suggest a design where every message in the social network is mapped to a username, even if it will always be some kind of user ID, and it's already denormalization. So. Because if the user decides to change the name, we don't want to update the whole database, and that's the problem with denormalization. So we always have some level of normalization. So the objects always, normally have some IDs, and you usually don't carry the modifiable object names with you, and that's basically is this denormalization. What is the actual probable difference between like traditional SQL database and transactionality, and what? At least I don't know any like big NoSQL database that this thing support. The thing is the transaction that could modify multiple tables, in a sense of whatever kind of tables you mean. So
well,
SQL
technically both Dynamo and Spanner can do it.
That's horrible. When they try to do it, that's horrible. It's something that you should always avoid, even if they technically claim that they can do it.
It's actually unclear. I mean, if you only modify like 5 records, I would say it's a really good idea to use the internal database technique, be it Spanner or Dynamo. as opposed to building your own two-phase commit in case something fails.
Okay.
I think a better example here would be
Dima, may I jump in to the couch again and say one remark that it's all what you're saying, it's true with the profile and so on, but effectively denormalization or level of denormalization really not resolvable if you have end-to-end relations.
That's a very good point. Thankfully, in most applications, many-to-many relationships do not have to be handled on an OLAP level frequently. But yes, that's a very good point. I think as a better illustration, forget social network. Let's say we're building Twitter, so you have the feed. I totally agree with Maxim that the last thing you want to do is to put username next to every single post. You would have user ID. So yeah, name is certainly retrieved in some other way. But then again, the mapping from the user ID to username can be cached in Redis without doing any joins, and the application code can just replace this before rendering the page. I think a better example of denormalization would be Twitter. So in theory, if you build Twitter over Postgres and forget algorithmic feed, let's say you always look at the latest tweets first, modulo some security, privacy constraints. In theory, you don't need to pre-populate the feed, right? If I open Lady Gaga's Twitter feed, just the only celebrity I know, then you can just run a select queries, give me top 20 posts, top order by creation time descending, limit 20. In practice, this query would be super slow. I mean, not super slow. It's probably indexed by timestamp, so it knows where to look. But still, it's a slow query. So in practice, for celebrities whose Twitter account is loaded frequently, it would be foolish not to maintain a cache of the top 20 tweets, right? In which case, the application layer would say, oh, Lady Gaga just tweeted. Lady Gaga is a celebrity. So what I'm going to do is I'm going to update this list of top 20, like 20 most recent tweets from her, add this one at the top, and remove the now 21st one from the bottom. That's, like, to me, this is a canonical example of denormalization, which on OLTP level you would almost always want to do in the application of this kind. I mean, it's just a canonical example where in the theoretical setting you're absolutely supposed to normalize the data. In the practical setting, if you argue with the core developers of Twitter that, hey, we have this normalized and fetching the last 20 tweets in reverse chronological order is a simple select query, so you should use this query because that's the best practice of using a SQL database, you will correctly get fired. It's just not the right way to reason about how to access this data. Just unmute yourself.
It only means that the database does not support this caching. So if your database knows about, like, well, if you have a DBI wizard that could set up all this caching in the on the database layer, then you just won. You don't need anything on the application level. This is just a question: where do you put this caching?
Right, but then the database can only cache so much. The moment I add some constraints there, such as, hey, if Lady Gaga has blocked me, I should not see her tweets. Or if some of the tweets are protected, so only those she follows can view those tweets. The moment you add these things, the caching logic becomes complicated, and I don't think it's plausible to rely on the database caching logic to do this right. I think it's a lot more reasonable to expect the developers to think of this caching manually, which is exactly what I'm trying to present, right? It's the demarcation line between what the developer does and what the database is expected to provide. Okay, I'm going to go further with this slide and past it. So it is somewhat not. So we did the bold parts. Now, it is not entirely true, but generally, what is cited as the pros of the NoSQL databases over SQL databases are two things. One is that NoSQL databases oftentimes are a lot easier to scale by just adding more nodes. Most NoSQL databases use key value stores, and as long as your key space is sharded, most of them would use consistent hashing. But honestly, any sharding logic would work, as in, if you just add more nodes, you use less RAM and disk on each node, which means your queries become faster. That's it. In practice, if you use a SQL database as the key value store and you add more nodes, I imagine most SQL databases, most SQL RDBMSs would be able to use these machines effectively. But again, from what I know so far, it's a correct statement to make that NoSQL databases are a lot easier to shard by throwing money into them. They also take care of replication level. So if your machines are dying frequently, NoSQL plus more machines is a cheaper way to ensure your data is never lost. And one more thing, which is not always a good thing, by the way. I actually think it's a bad thing. But NoSQL databases are designed to be REST-friendly and CRUD-friendly. Now, CRUD, that stands for create, read, update, delete, is one of those terrible building blocks, because on the one hand, if you have CRUD interface to your storage, you can do everything with it. On the other hand, if you have a database and the only way to deal with this database is CRUD, you'll be super slow for the vast majority of search queries, so it's highly not recommended. You'd have tons of round trips, tons of extra requests, but still, for small products built by a bunch of hipsters in a garage, CRUD is usually a good thing to have for your small first database. Note that I did not talk about SQL as a language yet. We have a slide for that specifically. Let's talk about databases design first. So I think the biggest, in practice from the OLTP setting, the biggest win, we kind of covered this already, but let me try to go through the slide. When it comes to OLTP use cases, the biggest win SQL RDBMS give you is transactions. When you need to change a few data points in different tables simultaneously in a way that they either all are changed or all are unchanged, SQL is often superior. A good example here would be a transaction that needs to check some permissions, update balances, transfer from A to B, potentially confirm the authorization token, authentication token, which could be a two-factor, which would be verified by a different service or whatnot. Unfortunately, most SQL databases don't let you write the code like this in a transaction. Andre would correct me if I'm wrong. Maybe Oracle supports this. Like, can I really write a piece of business logic which would have a transaction open for like 30 seconds until the user is typing in their second factor token? I would not be surprised if Oracle can do it. I know Postgres cannot.
No, but I think why cannot? It depends. Actually, it depends on the client setting, because if there is auto commit on or off. With Postgres, the problem on the clients that usually the parameter auto commit is turned on, and then every DML goes committed, and that's why the problem with the consistency. And not every clients work correctly with auto commit off, and that's another problem. So it's safer to do an auto commit on and just do that clean up yourself with the particular Postgres clients. My experience.
Hold on. It's safer for most cases where your requests are idempotent. But imagine you're talking money transfers, where you cannot double process.
Yeah. But you can always create a buffer area for that. I mean, you basically, if you cannot guarantee rollback, you have to invent it yourself in this case.
Well, yeah,
right?
that's the gist of my message. That's what I would like to dedicate most of the time of this episode to. It's all about this custom logic. You leave yourself a buffer, but you'll be inventing two-phase commit yourself. You'll have like, when I was talking about this in a different talk, I used the term mini escrow. If you transfer money from A to B in your database, you can have some internal escrow account. So you have A to escrow and escrow to B. If something goes wrong, the money hangs in this escrow account, which is ephemeral to the user. It's just your internal means to guarantee that you wouldn't double credit or double debit. But it's just a hack, right? It's just a hack to make it easier for you to not make mistakes while you implement two-phase commit. Ideally, ideally, you would use a database where you rely on this database's technique, on this database implementation and guarantees of transaction atomicity and replication. You would just write the code as part of the transaction, and part of this code would be an asynchronous call to a different service. And as soon as the service returns, success or failure of this two-factor verification, your transaction goes one way or the other. And you don't want this to be part of the application logic code. You want it to be part of the database code, so that if the database node dies, for example, you trust in the database to restart this code from the same place on a different machine. And I'm really curious if Postgres can, if Oracle can do it, by the way.
On a different
I
machine, I think no. I think it's not possible. In scope of RDBMS, I don't think you will meet this concept.
Thanks, Andre.
Sounds like you are talking. Sounds like you are talking about the long-living transactions. That basically the normal way to use transactions is you have a batch of a relatively short batch of operation that should be run as fast as possible, and finally it finishes. And in your use case, you want to start transaction, wait for seconds or maybe minutes, and then complete it.
Not quite, Maxim. That's half of what I would like to do. The other half is that I want this. Imagine the machine that runs this transaction suddenly dies in the middle of it.
Yes, and that creates. I agree. That creates a problem of. So if your transaction is not a batch, you have to be able to migrate this transaction and serialize it and migrate the transaction for reliability. If your transaction is fast, it's going to be fast, and it doesn't require any user input in the middle, you are just fine. You can just rerun the transaction on the new machine. But in this situation, this is not something you can afford. Basically, I think everyone is avoiding these design decisions. It's better to request a token, get the token, and retry. Start a new transaction, validate everything again, and then move on.
Right, but then I agree with you. Everybody is trying to work around this. But then, if you have a multi-stage transaction, if you have multiple parameters to analyze, your state machine, your state space would be a Cartesian product of those multiple dimensions. So if you have 5 dimensions of 5 possible states, it's almost guaranteed that your developers will forget something in the case of rollback, which is exactly like, so we have this ironic situation where on the one hand, when you're within the transaction, you can trust your database. Your RDBMS engine would do everything correctly with respect to atomicity and consistency and replication. Moreover, if your OLTP is fed from the bin log of this database, you just subscribe to the bin log and the update travels correctly to your OLTP database, to your data warehouse. Everything's perfect. But the moment you have to deal with a multi-stage transaction where stages are requested or serviced by different parts of your system, oftentimes different microservices, it's suddenly 100% on you to make sure you guarantee consistency in this case. At which point you're totally on your own. You lose all the protection of this database assetness, and you have to be as asset as possible yourself. And that's where all the bugs happen, right?
Basically, yes. You just have to split your logical transaction into a few database level transactions and guarantee that all the intermediate states are transactionable. So that is your escrow as an option. So the extra option that you have for this big logical transaction, you create an escrow state. An extra state in the same database, and you have a way to roll back or from to do the logical rollback. If you're thinking about, if you can split the transaction into just a few steps, it's that are linked linearly. It's relatively easy to reason about.
Yeah, look, I'm a huge fan of defensive programming, and since recently I'm a huge fan of defensive architecture. And I'm positive that if people like us design such a system, we would have those escrows or whatnot, and we would have simple rollback means. But then at some point, after we're gone from the company, somebody would come in and say, oh, you know what, I can do this better. I can do this faster. Nobody would let them to change our code. But then on their new piece of code, they would avoid the escrow and sincerely believe they've done a great thing, even though their code will contain a huge bug, which would sometimes get noticed. I really love designs and code that makes bugs visible right away. And having to implement your own two-phase commit, I think, is one of the best counterexamples to this. If your code has to be able to roll back the logic or the state machine manually, that's one of the examples of the code where even good engineers would often miss the bug. And so, anyway, the purpose of my talk, as I repeatedly stressed, and it's in the slides further, is developers are not good at rolling back distributed transactions, at implementing transaction orchestration, and oftentimes the modern architecture with microservices pretty much forces you to think in terms of how to distribute this transaction, which is super painful and which is best to be avoided. And one of the best ways to avoid this is to think about what should your database stack look like when you design the system. All right, moving forward. So yeah, we just covered this. Ideally, in a SQL world, you have a SQL RDBMS that would take care of all this transaction atomicity. In the real world we live in, it's not the case yet. In the NoSQL world, which is kind of what we just covered as well. Thanks for taking it 2 steps further. In the NoSQL world, imagine your databases only support CRUD or RESTful access. So no joins, no selects, updates, update if, triggers, conditions. You would effectively have to make all those changes yourself and roll them back yourself if something goes wrong. And if your microservice goes down and another node of your microservice picks the transaction up, you would need to have their transaction recovery logic custom built on your side, which is super painful. I'd like to highlight this concept of BFF, backend for frontend. It's kind of funny because in a way BFF is the people who speak CRUD and REST reinvented SQL transactions. They would argue that, you know what, the access pattern from the front end is usually performing these operations in certain order. Let's collapse them into a single API call, into a single backend call. Well, technically, SQL is doing exactly that, right? If it's a get query, you could get away with GraphQL. Not perfect, but it kind of gives you the guarantee that you can at least avoid unnecessary round trips. If it's the mutation, if it's a change request, well, BFF as a paradigm shrinks room for error, but it just forces the developers to implement those changes on the application layer on the backend. Better than front end, better than middle tier, still plenty of room for error. And yeah, I think the demonstrably most painful example here will be multi-table queries, as in joins. In a SQL world, that's just exactly where this RDBMS SQL engines shine. They would guarantee you no phantom reads, they would guarantee you atomicity, they would guarantee you consistency, they would just get the data for you, put it all together, and give you the final result. In a NoSQL world, if your transaction requires joining the data from multiple services, such as the auth service, validate auth token from login, validate second factor code, your state machine gets super bloated, and there's just too many ways you can screw this up. So yeah, keep in mind, developers are not good at orchestrating individual transactions. SQL level optimization is something what we kind of covered right away as we started talking about SQL. Yeah, the idea is that if your backend code is talking to the database using a SQL language, and your database itself is a SQL RDBMS, then tons of performance bottlenecks can be taken care of by the DBAs without touching the production code or without rebuilding or restaging the binary on a live system, which I'm not necessarily saying it's an awesome pattern, but first of all, it sometimes does help a lot. And second, it's an awesome illustration, I think, of how this demarcation line between developers and databases can be drawn. So it's really awesome if the language such as SQL exists. I'm not saying SQL is perfect for OLTP queries. In fact, I kind of think the opposite, to be honest. But the good thing is that if the OLTP, if the application layer to database, the OLTP language is SQL, this opens room for query optimization both on the application level and on the database level. And oftentimes, strategically, I would bet on the database level. I would bet on hiring better DBAs who can support your service to make sure it's up and running. It's usually a safer bet to scalability as opposed to trying to introduce more hacks on the actual application layer. In the slides, I'm citing a few examples of how could some database queries potentially be made faster. And I could easily think of an example where each of these 5 solutions would be the right solution. And if it's not implemented this way on the front end, on the back end, on the application server level, chances are your service won't fly. It just won't give you the right latency and throughput guarantees. At the same time, I think it's implausible to expect developers to think at this level. And if you can outsource this degree of complexity to databases and to the DBAs, chances are you'll be in a world where you can scale safer. I mean, of course, if you grow as a hockey stick, if you're a super successful startup, at some point you will probably hire people who know how to do it right, and you will probably have a roadmap how to migrate to a certain NoSQL custom-built key value store that is horizontally scalable because it's consistently hashed and it's pushing code to data and vice versa. But in most cases, when you're an early stage database architect, your job is to not think of this upfront. Your job is to make sure that if you start growing like crazy, your current design can sustain it. And if your current design allows for DBAs to fix things on the fly, that's a huge green flag, I think. It's a strong sign you're doing something right. And last but not least, when I said SQL in the past couple of minutes, we were talking about SQL as in SQL, SQL, RDBMS, the database engine. Somewhat unrelated in the modern day to the very engine is the SQL language, the structured query language, the data language we use to query the data. I honestly don't think SQL as a language is anyhow close to SQL as the RDBMS engine these days, because Hadoop query language is almost entirely SQL. Google BigQuery supports SQL. Snowflake supports SQL. So the line between SQL as a query language and SQL as a database paradigm and implementation is kind of blurred. So I think it's important to highlight SQL as a query language into its own realm. But hey, I do feel like saying that SQL is, I believe, the most widely used functional programming language in the world. SQL is a functional programming language because you don't imperatively tell I was about to say the compiler, but there's no compiler. So the language is functional because the way you write the code doesn't necessarily describe how it should be run. It just describes what result am I expecting, and it by design gives the engine the flexibility to run the query in the way it considers best. On this note, I would like to stress that the most widely used declarative language is likely PCRE, per-compatible regular expressions, which is kind of funny. Old school things are still surviving to this day. So yeah, moving on from the SQL as a language. I found this slide as a good example. I think if I click here, do you guys see my screen?
Yeah.
I mean, you're not seeing the slides, right? You're seeing the diagram. So it's just one of the good examples of a somewhat non-trivial business logic. I don't think it's super complicated. It's famous enough for people to recognize it. It's the logic by means of which Slack, the app, decides whether the user has to be notified about the new message. So now, Imagine every single branching point here is a request to some microservice or some database. Channel muted, yes, no. Look up somewhere. User in do not disturb mode, yes or no. Look up somewhere. Imagine you have to write the code that checks these preconditions and follows this flow chart. Well, first of all, it would be super slow. You would have a round trip for every single arrow. You will probably cache some results. You will probably make some requests up front, but still, it's a super non-trivial flowchart to follow. Imagine the world where this whole diagram. I mean, let me describe this from another end. Imagine you don't know this diagram, but you're given full access to Slack source code, like you're an auditor. How long do you think it would take you to draw this diagram based on the code? I bet it's non-trivial at all. In a perfect world, the logic like this would be written in a language which is so structured that you could just pipe it into GraphViz and have this diagram pop out, right? Because effectively what you would like to see is, hey, I have this state machine with certain conditions and certain steps. Extract state machine from this query and plot this for me. So even though it's not 100% related to the very topic of databases, SQL versus NoSQL, I think the very idea that the code these days, like this is actually the design doc. This is the result of multiple iterations. I'm pretty sure some changes were fairly painful because the product designer can just change one arrow and the engineers have to change everything from the code to the database structure. But fundamentally, we do live in the world where this design has nothing to do with how the code reads. And I think fundamentally it's one of the dead ends we as the architects face in the modern state of the art of database design. So I do hope to live long enough where the programming language for a logic like this would be as simple as this flowchart and would pretty much compile into the query. And it shouldn't really matter for the developer whether a particular yes/no question is a call to a certain microservice or an RPC call or an asynchronous message bus request response or the database query. And it shouldn't really matter to me which of these queries can be combined together because it's as fast to get 3 answers than it is to get 1 answer. So I might as well just request 3 answers up front to save time. It's just an example of where the application layer logic becomes complex and hard to follow, and we, the architects, have done nothing so far to make it better. I'm almost reminded of this humorous conspiracy movie. They made a joke on the 1st of April many years ago. It's like a 15 minutes plot, which is humorously trying to portray the message that engineers rule the world, but they do nothing all day. They just get paid tons of money because it's so simple. Well, it's not simple, and it's not simple for a reason. And the reason is we don't know how to make it simple, but we should. And with all this being said, this is not 100% related to databases, but I think it hits close to home because the complexity hides, as most of us would agree, the complexity hides in the way the application logic talks to where the data is, which I refer to for the purposes of this conversation as the database or the OLTP. I'm going back to the slides. Yeah. So yeah, as I just said, if it's an if statement or a state machine transition, it will be really hard to follow. So I started all this preparation, all these 16 slides, not to mention the starting one, to outline that I honestly think that in order to reason about this as an architect, the best mindset to have is think of the demarcation line between the database, everything that is a database, and the application logic. Again, everything that is the application logic. The application logic includes all the micro or macro services, all the load balancers, all the message brokers that have their own message delivery rules, all the retransmissions on your Rabbit or Kafka or whatnot. And the database includes all your relational and non-relational, SQL and NoSQL, databases, all the caches, all the, again, persistent message queues. And if you can design it such that you can, if you can design a business logic such that it leverages the transaction mechanisms of your databases, which you can trust, such as Oracle or Spanner or Dynamo, Postgres, or even Redis, by the way. Redis supports transactions in some way. If you can leverage this means, by all means do it, because it's going to save you tons of headache. On the other hand, if you cannot use them to their fullest, if you feel like you have to design some two-phase commits, if you feel like you have to design distributed transactions in the software, in the implementation of your microservices, then your best bet is to keep the database layer as simple as possible. Keep it simple, and just all the logic will be concealed in your application layers, which you can test independently using extensive regression and stream testing. If you have both parts, the application layer and the database logic, if you have both of them convoluted in some clever ways, there's a good chance that you would win something in the short term, but this code would be unmaintainable, to say the least. So yeah, my point is really, when you're thinking of how to best combine databases and caches and stuff like that, imagine that the developer who comes a year later does not know what a distributed transaction is, and they would reinvent it, oftentimes incorrectly. And the best architecture is the architecture which protects you from this kind of failure modes, because the failure mode is not that the database is failing or your message bus is losing messages. The failure mode is new developers assuming that they know what they're doing, but in reality, your custom rollback logic was a lot harder than the actual business logic. It's one of those cases where, in the modern world, works on my machine means nothing, because it's easy to have the happy path do the job. It's kind of impossible to guarantee that your distributed transaction does the job. I've realized all this when I was reviewing endless concepts of literal actions, and I know something about Paxos and Raft, and even those, Raft is simple, but even in Raft you can make tons of mistakes to make sure it, and these mistakes would go unnoticed, because people think they understand it, but their room for failure is just too wide. Paxos is hard to understand. I'm positive that database transaction isolation implementation is super hard internally, but the good thing is that it's built many years ago by people who know how to do it for dozens of years, so this you can trust. Thinking you can build something of comparable robustness is just crazy. Rant over. All right, I think it's the second last slide, or second last slide. So again, in the architect's corner fashion, we should talk about the common pitfalls. One thing people often say is, "Oh, I'm near capacity. I'm just going to add more shards." And well, if you have one shard and your queries are often single key, there's a good chance 2 shards would give you nearly 2x performance. But if you have multiple cross-shard requests because you have to perform some joins or whatnot, and you already have 20 shards, there's a good chance that 21st shard would make it slower. In fact, there's a good chance that going from 20 to 15 would make it faster. So I think a good heuristic is to think of sharding similar to how you think of caching. Caching really helps. It gives you a huge boost, but it cannot cure all the problems. Same is true for sharding. Sharding is kind of better for NoSQL databases because they are, by design, distributing the data over some evenly spaced hash ring. So they would naturally be better at utilizing more CPUs available. But again, the moment your queries begin accessing multiple keys, your bottleneck would very quickly end up in a few shards and a few keys, and you'd have to think about how to work with these keys in some custom-built ways. It's actually a popular interview question, for the record. How do you deal with a case where your NoSQL database is super fast, but you have a really hot key, so that every third query has to hit this key? With NoSQL databases, I'm not sure if it's a good advice to be given overall. Yeah, go ahead. Just unmute yourself first, Rahul.
I think I raised my hand by mistake. I'm sorry.
Could you say it again, please?
I think I raised my hand by mistake. I'm sorry.
No worries. So I was about to say that, moving on to the second point, I'm not sure if it's a good advice to give in general, but I feel like in most cases, because handling distributed transactions in a manual custom-built way, it's so hard, and because custom rollbacks are so hard, I think in the vast majority of cases, the first question you should be asking yourself if you have to do it is, what's my cost of error? What's my cost of failure? Because yes, if you want to be 100% reliable, you have to build a lot of clever things. But first of all, machines don't fail too often. And second, let's say a machine fails often, frequently, let's say once a year. What could possibly go wrong? Some users are logged out and they have to log in. 0.001% of your uploaded content or posts or comments are not posted. Or what? You suddenly give the users extra money they should not be given. In many cases, these things are not too expensive, whereas building reliable software that handles these cases is remarkably expensive. So as an architect, as a nerd, as somebody who likes technology, I think it's nice to build near perfect software that handles all the cases. In practice, oftentimes, I think cutting the right corners is a better solution. So yeah, my heuristic here is, if you're thinking of implementing a custom-built rollback for your custom-built two-phase commit, either you know exactly what you're doing because you've done it before, or you're doing something wrong. Talk to somebody who has done it before, or find ways to not do it. Moving on, to achieve high availability, there are tons of standard techniques. None of them guarantees success, but most of them are good enough heuristics. So you would probably need to use most of them, and even used improperly, they would still improve your system dramatically. So the obvious first example is idempotency tokens, request IDs. So if you're building a bank and the user clicks send $100 in the browser, generate some browser level random string and attach it to the request, so that if the user clicks that twice, or the browser crashes, or the internet dies, the server would be able to figure out that it's the same request to send $100, because the token would be the same. When you have asynchronous state, when you need to wait for something, when your application business logic is a bunch of callbacks, if your application can die and the callbacks will be hanging, one cheap solution is to keep this asynchronous state in an external cache. Redis is surprisingly good for that. It makes your application substantially slower compared to bare metal. It would not make it slow for the user, by the way, because Redis is still faster than the database. But you can use Redis as the cache. You can use Lua as a transactions engine for Redis. Redis is certainly more reliable than your application in most cases. So it's a cheap way to, and Redis has its own replication engine, so you can have your own Redis cluster. So it's a cheap way to make sure that recovery is, not to say easy, but it's a cheap way to make sure recovery is possible. So if you design with this assumption, you'll do well. Rahul, if you keep your hand raised, you'll be on my screen. Now you're off my screen, and you're gone again. Well, I'll keep going, but don't hesitate. What else? Yeah, two-phase commits, painful parts. And one more thing I have to highlight is, so no code is perfect. If you're an active C++ user like I am, you will probably design your data model internally in your application so that there are no memory leaks. Memory ownership is clear. If you're not a good developer or if you don't pay enough attention, there's a good chance you would have some memory leaks, which again in practice is not too bad of a deal. It's just painful. If you use multiple databases in an imperfect way, you would have data leaks. You would have like asynchronous contexts that are not cleaned up. So at the very least, have a habit of having some cleanup jobs. They would at least tell you, let's say once a day or once an hour or at least once a week, hey, I have this hanging asynchronous contexts in Redis, in my database or whatnot. Well, first of all, just knowing they are there gives you a good idea of what could go wrong. Second, you can just correct them. Like if you're in, I don't know, an e-commerce site, if some order didn't go through, you know which order didn't go through. Send an apology email, give people a gift card, move on. In practice, you can even design your system so that some not too happy paths are dropped by design, and they're picked up by a cleanup job that runs every, let's say, 15 minutes, which is also suboptimal, but a lot better than not handling those cases. Moving on to the last part, the things that I think, okay, if you unmute right now.
What would, I am unmuted, I think. So it's like between Redis and Memcached, which one is like better? I know Redis has, support for additional data structures, and people who do rate limiting, they use Redis, the sorted set in Redis to like do the sliding window rate limiting. But if for simplicity, like Memcached seems better. So if someone were to ask, or like if I have to make a decision, how do I make this decision?
Any takers?
Well, I can say that a couple of years ago, I joined the project, and that I'm still working now as kind of an architect, more or less. And the trick was there is that it was first time, I think, in my life that I've built the system from the scratch. So literally, the only solution that was chosen was the backend solution, so where we put our data. So from that angle, we started to build up the thing. And the choice of the technology is actually a headache, because you can do one thing with millions of ways, and all those like things will work at the end with some pros and cons. You know that will work, and how to do it fast and efficient, that's the question. I do like the thesis that Dima told a couple of slides before, that systems that were written long time ago, for instance, people say, yeah, if we would knew that, we would probably did it another way around. Like known mem by the historical reasons, we have this piece of code. Or this solution, I do like that, because in principle, when you prototyping or building from the scratch, I suppose that almost inevitable, you will get into troubles one way or another. So you have one decision in 2 steps will lead to performance, or one decision in 2 steps will lead to something not supported that you thought it supported. And then you cannot just step back. You have to use that one, because lots of things that are already written is working fine. So my guess is to try to identify technologies for their purpose. So for instance, like if you know that you need the transactions and you need to support transactions, you look to the RDBMS site for the solution that you can cope with. So Oracle is expensive, but very good. Also, I mean, if we talk about the databases, in principle, one of the decision point is backup recovery. I mean, solid backup recovery is a crucial thing, especially in transaction world. So,
hold on, Andre. I think.
Okay. You have another slide.
I think Rahul is asking specifically about caching.
Yeah, but again, so Redis, in that sense, I think it's a great solution for what it was designed. So in-memory thing with the simple interface and simple storage, also with potential of clustering, it's absolutely a great technology. So if you're not certain like what to choose from, I think Redis already proven that it's quite like solid solution for many use cases. So you just take the experience and say, okay, that works for many people in the similar tasks. Probably that will work for us as well.
Let me try to add to this. So I actually realized, I'm thinking, when would I seriously recommend Memcached over Redis? Because like intuitively, I think Redis can do everything Memcached does and much more. And so I can think of two things. Actually, I can think of three things. One is Memcached is natively least recently used. So I don't think Redis supports it out of the box, or at least I'm not aware of that. So if your task is to give it 4 gigs of RAM and make sure it uses 4 gigs and not a byte more for a cache, I think Memcached would do it for free right away. Another thing is, I think, is Redis. Memcached is easier to integrate on the Nginx or Apache level. It's designed to plug into this pipeline right away. The third thing is, I honestly don't know if Memcached supports it out of the box, but I think it would be easier to scale cache across machines, because Memcached would have multiple solutions available. Either it supports it out of the box, or you have some standard ways to shard Memcache. I mean, caches can be sharded natively. Now, but again, for caching, honestly, I don't believe in caches that much. As in, you can always build a cache yourself. It would not be that hard. Cache is not something I would totally recommend using an external tool for. When it comes to something beyond caching, such as different data structures, such as Lua transactions, such as replication, that's why I would certainly use a database, or kind of database, which Redis is and Memcached is not. So the bottom line is, for a simple cache, I can see why in some cases Memcached could be better. The moment you want to use it for something else, custom data structures, transactions, replication, use Redis over Memcached and don't look back. That's my top level intuition. And yeah, I think what Andre is saying, I'm totally plus many in this. Yeah, sometimes old school tools are really the best. Memcached was first written by, I think, Brad Fitzpatrick in PHP for LiveJournal, and then it was rebuilt by Anatoly Vorobey in plain C, not even C++. So I'm fairly certain for simple blob storage is remarkably fast, probably better than Redis by benchmarks. But again, in my head, caching itself is easy, and it's not really worth talking about much. And what is worth talking about is custom built data structures. Like, I mean, for example, I'll give the word to Maxim. I can see. Yeah.
Yeah, I just want to put like a few words. It's actually a good question, not only related to this choice. I guess it's related to every technology with which has some analogies. For example, this database or this. For example, this one is simpler. This one is more powerful. But will I need that power in a year, in a two? And will it be easy to migrate? And also, like in this case, okay, it could take Memcached, but okay, in 2 years, it would lead to a huge refactoring. And I guess it's a guy, an architect like you, it's his responsibility to predict the decision and maybe then make a choice, because it's like more, how to say, not even a political choice, but you got to predict the future and then make this choice.
Yeah, you got to exercise your wisdom. Huh? I mean, really, I don't view Redis as a database. But on the other hand, we have to give it the credit. Lua, as legit engine's transactions. Lua as the JIT engine for transactions is actually making Redis a fully serializable database that is totally atomic and super high performant and supports replication. So if you want to change 2 keys and maybe insert into a third skip list, priority key or whatnot, based on the condition of the 4th key, in Redis Lua, it's a 4-line script and it's effectively a transaction. And in a way, that it's a more powerful transaction than, sorry, Andre, than what SQL databases can do. Because, I mean, it's different purposes, right? Redis can do this at tens of thousands of queries per second. And for some applications, like you can build your backend on Redis. The application server is just calling those Lua procedures in your repository. In your Git repository, most of the code will be Redis Lua and some unit tests in, I don't know, Go or Rust or whatnot. So yeah, but again, that's a database use case of Redis. When it comes to caching, I'm just no expert, but I don't think. I mean, it's also important. Yeah, I guess I'll make the last philosophical point here. It's also important to dedicate your time to the right problems. If you're debating about between 2 options and there's no clear winner, chances are they're both good. So it's not worth your time as an architect to spend a couple of days talking about Redis versus Memcached. Because if you're debating about this for 2 days, if you make a mistake and pick the wrong one, the cost of this mistake is so low. Your time is better spent on other things. And so the cost of mistake is low in that you wouldn't lose much for your product. And it's low because if you need to change between Redis and Memcached, it's still a somewhat straightforward change. Changing a cache is a lot easier than changing from SQL to NoSQL, for example. So yeah, I hope I answered the question, Rahul. Okay, so 2 more points to make. One is I actually added this later. I added this today. Don't neglect the cloud solutions. It's a huge point by itself. There are 2 religions. Religion number 1 is I want to be cloud agnostic. I want to be able to support hybrid cloud, my own cloud. I should not tie myself to any vendor. And I like this approach a lot. But on the other hand, the cloud is here with us. It's not going anywhere. And oftentimes, if you have a lot of money as a company and the cloud offers just what you need, using Google Spanner or AWS Dynamo may well be the best bet for you. So it's a big decision to make. It's not architectural. It's, as Maxim said, political. But if it can be made, a year ago I would be like, not to say strongly opposed, but I would always argue that hey, I want a full cost benefits analysis just because I feel like these guys can raise prices tomorrow and we need to have a backup plan. These days I'm more and more inclined to let it slide, as in if we have a long-term contract with one of the providers and we have the need for a service that they do offer for a fee, it may well be the best solution. And it's easier to maintain it in the future, easier to hire people who know how to use it. They would probably be improving their service, so there's a good chance they would solve our problems too. So the pros begin to outweigh the cons. And one more thing to mention is NewSQL. So the cloud solutions that I think are worth mentioning here is DynamoDB and Google Spanner, Amazon DynamoDB and Google Spanner. For Dynamo, do watch this talk by Rick Houlihan. It's an awesome talk. Rick talks a lot about why should you unlearn what you learned about data normalization, because statistically you can build a lot better NoSQL schema. There is such a thing as NoSQL schema, so that your key value distributed store with some support for transactions can be a super high performance backend for your needs, and it also scales for free by just adding machines. So it's a really good talk, mostly common sense, nothing internal, and you learn how much have you been missing if you have not been fully into NoSQL databases like I was. Google Spanner, again, the more I learn about databases, the more I fall in love with Spanner. Google said screw it, and in their data centers they have their own atomic clocks. It's actually 2 clocks, atomic plus GPS. They have different failure modes, so cumulatively these 2 together have low drift. So what Google does is I think Maxim Maxim can talk about this better, maybe. Maxim Ryzen. You appeared on my screen. Well, it's okay. I'll continue, but feel free to interrupt and correct me. So what Google did is they said, screw this. It's actually possible to build a cloud scale, infinitely scalable RDBMS with 100% serializable transactions, perfect isolation, perfect durability, and it's strongly consistent. So it's you deal with Spanner as if it's a single machine database, whereas internally it can be cross machine, cross data center, cross continent, and the data is reliable and transactions are supported. The true time. So there's this whole conversation about exactly ones and Lampert clocks and vector clocks, and how do you make sure that if A happens before B, but some observers saw B before A, how to fix this issue? It's actually a really, really hard problem. One of the best solutions, which is super hard to implement, is to say, I'm going to ignore the problem and just make sure every single change to my system has the sequence ID. So I'm gonna serialize, as in serial number ice, linearize every single change to my system in a fixed manner. Many databases do support it, like Redis has epoch index. Spanner just said, you know what, we're going to have our own hardware clocks that are reliable, and we're going to have timestamps from these hardware clocks. And because we synchronize hardware clocks down to, I think, on average 4 milliseconds, up to 7 milliseconds across continents, we don't need to cross-check everything, because if something happened more than 7 milliseconds by that machine's time, it's in the past for me, and vice versa. So they've done a lot of work to make sure the database looks as if it's a single machine database next to you, but it's actually super distributed. It's remarkably expensive. So building a database, building your service on top of Spanner in GCP will cost you unless you plan ahead. But again, in many real-life use cases, it is actually quite a worthy route to take. Any additions here? Okay, I believe it's the second last slide. NewSQL is a term that is just being coined. I don't think it has earned its place yet. There was a company called Memcached. It's now rebranded as Single Store, and I think they IPO'd via spec just a few weeks ago. The claim was that we can build a better SQL, and way before they were this big, they just realized they built a good enough SQL engine so that Morgan Stanley and Citibank were using them in the backends. So the claim is that in the modern world, where this database versus application logic dichotomy is painful, the claim was that there is room for the cloud SQL solution. For the cloud, NoSQL engine that can pretend it is a SQL engine successfully. So it's not a relational RDBMS. It's quite the contrary. It's a white columnar store. It's tons of denormalization behind the scenes. But the claim was that we can build a system that is expensive, requires tons of resources, but it's just SQL for you, and it does all the job. And this company started emerging, and they are doing quite well. So the bottom line is, if you feel like you could use a large-scale SQL database, but you don't want to be tied to any cloud platform, there are solutions that are SQL compliant and cloud level distributed. They are emerging, and I think they are the future, more or less. I don't quite see the world in which SQL goes extinct, even though I blogged about this many years ago, that SQL should be pretty much gone by now. Well, it's not. Okay, and this is the very last slide. I think we covered most of it. I think I should only mention that really the main takeaway I have is hold on. I'm being kicked out. Okay, so I think the main takeaway is that once you define the database in the OLTP sense, in a generic fashion, the main takeaway is that database versus application server is the dichotomy, and it's a source of pain for pretty much most of development work these days. So solutions are emerging. The world is not staying still. And even in the past 5 years, quite some progress has been made. But I still think that for the next 10 plus years, we're still going to live in the world where small teams create cool stuff, oftentimes by doing miracles, hacking their way through, ignoring the best practices and the separation line between application servers and databases. And then most companies would fail so that we would never know about them. Some will succeed, some will grow super big, and they would be the driving forces behind new database technologies and people who understand the first principles of how to split this work between databases, message queues, caches, transactions, RDBMS as in relational database management systems, NoSQL databases. We would keep being in demand because that's still what most of the bleeding edge work in the next 10 years would probably be about. I do not anticipate some miracle database that just revolutionizes everything. Even though I can think of how it should look like, I can think of how it would look like. I don't think it's anywhere near. And yeah, the second biggest takeaway is if you only know SQL, do take a look at NoSQL. That talk by Rick is awesome. If you only know NoSQL, do take a look at SQL because transactions and isolation, that's a superpower which takes away tons of pain from your application level business logic. And yeah, I guess that's about it. We should absolutely do some Q&A or whatnot.
I don't have questions. You left all decisions to us.
I have some questions. So my question is around columnar databases, which fall under the category of, I reckon, NoSQL. It's like, in theory, what I've heard is that if you require very high write throughput, you should end up using, an HBase or a Cassandra versus a traditional SQL database like Postgres or Oracle. My understanding of this is just theory. Is there anyone here who's in practice experienced this or done this, have used both Postgres and something like Cassandra or HBase, and noticed that write throughput is indeed higher in the latter?
Okay, I can try. So first of all, I wouldn't phrase it exactly as you phrased it right away. There's no requirement to use Cassandra or HBase for high throughput updates. There is a requirement to use I wouldn't even say NoSQL. You would have to use some key value store over a really, really large hash space of keys, which you could shard across multiple machines. That's the must, right? If you need to support billions of updates per second, billions of reads per second, that's the only option you have. But then it's not really a question about how do you best it's not really a question about how do you best combine this with relational databases. I mean, you can always have the custom logic on your application level that would group transactions, batch updates. So you would have a single update per key in your Cassandra or whatnot. And then for every, 50K of those updates, you would make a transaction into your Postgres. I didn't have these issues in my life because I just know that if you have this number of requests per second, don't do a relational transaction per request. I have seen designs where people manually shard relational databases. I've seen designs people say, hey, I have these microservices. They are shared nothing. So you can add them as you please. They will just reshard the key space. And each of these microservices is a Docker container that is my own code plus a Postgres instance, which would in a way be the best of both worlds, right? On the one hand, it's kind of Postgres. On the other hand, it's super sharded. But yeah, I don't think the thinking should be, oh, I have this many updates per second. It should be Cassandra or HBase. I think the thinking should be, I have this many keys accessed simultaneously, and they don't work with one another on my business logic level, so I can shard them. Whether you shard the database and just use a load balancer to update the shards correctly, or whether you shard your own application servers and have your own cache there, that's immaterial to me. The issues begin when you start running queries which span multiple of these shards. That's where the system design part comes into play. That's why we would need to think, oh, do I need to, if I have like 100 shards, do I have 100 squared pipes between them because they need to talk to one another? Does the sender of the message know where to send the message, or do I rely on some RabbitMQ so that my receivers will subscribe to their own shards? Those are hard questions. But on the very question you asked, I've never had this issue.
By the way, could you provide few words about graph databases? Is this like a good benefit having like joins in relational databases and some benefits from NoSQL? What I know is that they have it like a constant time accessing related, not related, like linked data and so on. So it's like a join, super fast join. But on the other hand, it's more NoSQL database. So what is good option to use this one?
I asked this very question to the guys who built modern NoSQL databases when it was still possible to meet them in person. And because I still don't fully understand what a graph database is. And for the record, graph database has nothing to do with GraphQL. So the answer I got, which kind of makes sense to me, is that graph databases are optimized for graph traversals, as in, if your queries are mostly of the kind that traverse the graph database makes it same complexity to make multiple hops as it is to make one hop. So you can pack a graph into a normal database, into a relational database, right? You can have the row of the SQL table where the node key is the primary key, and you have the children. You have a bunch of joins. But then if you want to do something like, oh, look at something that is at most 4 hops away from me, it would not be a single query. It would be kind of writing a recursive function. So graph databases have their memory layouts and disk layouts optimized for these recursive functions to be run faster. So for them, they try to collocate the nodes, from what I understand, so that making 2 or 3 hops is about the same complexity as making 1 hop. Whereas if it's a SQL world, or if it's a CRUD over a NoSQL world, you would have to make custom requests so that's more round trips and you hit more nodes.
Looks like it's for such analysis cases like we use OLTP databases, like to build all those indexes and then do a bunch of analysis and so on.
I have not had a case for a graph database in my life, so I can't really answer this.
Okay.
For Columnar databases, ironically, in my original script for today's event, I had columnar databases as a sub-concept, but as I started growing deeper, as I started going deeper into what has to be covered, I realized on the system design level, on the architectural level, it's not really that important that a database is columnar or not. So in most cases, you know which database to pick based on the standard existing benchmarks for those. And if you have to build your own database, well, that's where you have to design columnar first or documents first. But if you have to build your own database, it's a whole different conversation, right? And once again, in the world of denormalization, you can always pack more things into the same column. So a good example, again, from Rick's talk is if you need to potentially query, let's say, vendors or products by country or country plus state or country plus state plus category, you can always construct multiple keys in which you concatenate different features together. In which case, looking for products in certain category in this country and state becomes looking for selecting all database rows that are in this particular key space of this particular key, where the key is predetermined to be country concatenated with state concatenated with product category. And you can have many of these columns because, again, these days RAM is cheap and machines are cheap.
Well, it sounds like to reading a data and code book from the back to the front.
Well, it's more like in most books you have the index at the end. It sounds like for one book you're writing, you also keep 100 books where you write things in different places, so that for most of the search.
No. I meant that in code, the data structure and base, it's all started that, well, it's not so good that you store it in all in one line, so let's split it and normalize it.
Well, yeah, that's the beauty of NoSQL these days. The world is going full circle. That's what I'm saying in the beginning. In order to understand NoSQL, you have to unlearn what you have learned, because the trade-offs have changed. There's no longer need to save on disk and CPU. The need these days is to make sure you can serve higher throughput with low latency and be scalable, so that you can always throw more money, add more machines, and win those few milliseconds. It's a different world, and yeah, I had to wrap my mind around this for a while, but then I realized it's fun. That's what makes architecture fun. It's like thinking about designing gas vehicles for 50 years and then realizing electric is the future. I'm not saying gas cars are bad. Electric probably is the future.
By the way, 2 words about this electric versus gas. Just a few days ago, I saw a video with a total calculation of energy loss on each step, delivering energy like to electric vehicle and to gas machine, and the, how to say in English, like KPI. So KPI of gas machine is twice more bigger than an electric. Today, maybe in the future it will be even better.
Output ratio. That's true, but don't get me started on this conversation. Thankfully, it has nothing to do with system design so far. Okay, what else can we cover? I think it was a quite long episode. Hopefully we enjoyed it. All right, so let's call it then. Thanks, everyone.